G'day team, welcome to this video on Kaplan-Meier curves. It's a long-awaited video in this survival analysis series. For the rest of the videos, you can check out zedstatistics.com, or I'll put a link to the playlist in the description of this video. But let's get stuck into Kaplan-Meier. And this one is going to be good, team. Not that the other ones aren't good, but I'm excited for this one because it's such a commonly used estimator, and it's essentially the bedrock of survival analysis. So understanding this is key to getting your head around survival analysis generally. So as always with these videos, I'm going to start off by looking at the intuition behind Kaplan-Meier estimation. And if you're a first timer on survival analysis, that's going to be a really great section for you to understand the foundation of the estimator and how it's calculated. The next two sections will be quite statistically rigorous. I'm going to look at confidence intervals, so that explores the uncertainty behind the Kaplan-Meier estimator, and also the Logrank test, which compares two different Kaplan-Meier curves for different subpopulations. So you might want to compare males to females in terms of their survival experience. And finally, I'm actually going to conduct a Kaplan-Meier estimation using R software, which is freely available. So it's something you might want to look at if you're needing to do a Kaplan-Meier estimation and wondering how you even get started. So if you want to jump forward or back at any point, I'll put the timestamps in the description. But it should be a good video for both beginners and for people that want a bit more statistical rigor. Anyway, enough blab from me, let's get into it. Well, the first thing to note is that Kaplan-Meier, this estimator, is a non-parametric estimator of survival, and it dates back to 1958, where two statisticians, Edward Kaplan and Paul Meier, were independently coming up with this exact same thing. And the editor of the Journal of the American Statistical Association, that being John Tukey, and that's a real photo, by the way, he convinced them to join forces and create one paper. And that paper was really the birth of what we now call survival analysis. Now, what do we mean by non-parametric estimator? Well, you might think of survival as something that might look a little bit like this, where if you're infected with some disease, you might have some kind of survival horizon that looks a little bit like this, where as the months proceed from that first diagnosis, your chance of survival kind of slowly curves out like this. Now, to make a really nice smooth curve, you're going to need something called a parameter. So for example, a normal distribution will have a parameter of the mean and a parameter of the standard deviation, which describes that bell curve. A curve like this might have a couple of parameters to describe that slope. But that is not what we have here. A Kaplan-Meier estimator looks a little bit like this. And if the steps become kind of small enough, it does resemble a curve, but technically when we call it a Kaplan-Meier curve, it's not strictly a curve. It's more steps than anything else. Nonetheless, we do call it a curve, and it doesn't rely on any parameters. It instead will use the particular dataset that created it. Let's explore this with an example. So we're going to use in this video an example of wombats being infected with mange, which is a terrible disease that wombats get, and they're struggling with that in the Australian bush. So the question is, how long do wombats survive once they're infected with mange? Now, 10 wombats in an infected community were followed over 3 years. This is as simple as it's going to get for examples of survival. 10 observations. We're going to see what happens to them. So here we go. We've got 10 wombats, A through J. And on the left here, we can see that we have their infection start time. So wombat A was infected in January 19, and the end time of the infection was April 20, such that this wombat survived 15 months, as you can see. This final column decides whether this wombat died or whether it was censored. Now, in a previous video, we discussed what censored means, but appreciate that this first wombat did in fact die after 15 months. So that's April in 2020. The second wombat was infected in February 19, And the end time written here is September 2021, giving a survival time of 31 months, but this wombat did not die. It just so happened that this wombat reached the end of our sort of monitoring period and it was still alive. So we're still going to count this wombat in our data set, and it's really important for us to count that because it's 31 months of survival once this wombat was infected. We don't know how many more months this wombat survives, but we know it survives at least 31 months. So this last column defines for us whether this wombat died or whether it was censored. And we can continue on for all the other wombats, C, D, E, F, G. So you can see it's a nice jumble of wombats that died and were censored. If we're going to look at the plot here in terms of the survival visually, you can see that Wombat A starts at January 19. That's when we know they were infected and died. That's a little cross. The cross means that they died at that period. Wombat B survives a long time, and we've got a naught at the end, or a circle right at the end to say, yep, this wombat actually didn't die in September 21. We could not follow it up any further. So you can see how all this works. There's Wombat C, D, E, F. F has got a short lifetime. What's that? June 19 to October 19, so only 4 months of survival. This is all looking pretty good. It looks like the kind of stuff we were looking at in the first couple of videos of this series, looking at censoring, etc. What we do is we actually then order the wombats in terms of their survival time from lowest to highest. So F was our, well, shortest surviving wombat at only 4 months, then G at 6 months. Then we have J surviving for 8 months, even though it was censored. And you can see we've then listed them from F, well, down through to B. It's a nice jumble of all the original wombats. So how do we then create an estimate for survival? So we've got that table again here on the left, and we're going to create a new table where we calculate the survival amount in terms of the proportion of wombats that have survived to each time period, or through each time period. Now, as we go, we'll progressively be creating a little Kaplan-Meier curve here on this plot. So let's see how this pans out. I'm not going to show you the formula just yet because I want you to kind of intuit the formula as we go. So to start with, from time period 0 up until but not including 4 months, there were 10 wombats alive. That's what N represents. That is the number of wombats at risk at the start of the period. D is the number that died at the beginning of the period, taken out of the number at risk. So given that we had no deaths at time 0, the calculation is trivial. We have 100% of wombats still alive. So the survival is 1. So we can put that in our table and also draw a bit of a line all the way along from between 0 and 4 months across the top of this survival curve. From time periods 4 up into but not including 6, we had 10 wombats that were at risk and 1 died at the start of the period. So our first wombat, Wombat F, died at time period 4. So what's the calculation for the survival between 4 up to but not including 6? Well, you're probably going to intuit that it's got to be 90% survival, right? 1 wombat died out of 10, so 9 will have survived between these 2 time points, right? And you'd be right. So here's now the formula for the survival of a Kaplan-Meier curve. It's the product of N minus D over N. That's the number at risk minus the number that died divided by the number at risk. Before we figure out how this product works, let's just try to apply that to this first row. So there were 10 at risk, that's 10 minus 1, so that makes it 9 over 10. Now the product means we're going to multiply this by the previous calculation, which just happened to be 1. So we know that from 4 to 6, and we'll put this on our plot now, from 4 to 6, we have 90% of our wombats alive with us, right? That seems fairly straightforward. What happens with the next one between 6 and 8? Well, there were 9 wombats alive at time period 6 because 1 had already died. And of the 9, 1 more did die. That's Wombat G. Wombat G died at survival time 6. So it's going to be 8 on 9. And we're going to multiply that by the previous fraction we got, which was 9 on 10. So that's what that product means. It says multiply this fraction with all the previous fractions that you've calculated before this, which will give us 0.8. And again, that makes a lot of sense, and this seems like we're overcomplicating something that's very simple, right? Every time a wombat dies, we lose 10% of the wombats, right? Well, it's right up until this point, but now it's going to get a little bit more interesting because at time period 8, we don't lose a wombat by death. We lose it because it was censored. So there was 8 wombats at risk at the start of this period. One of them disappeared, but it didn't die. If you try putting this into the formula, it's going to be 8 minus 0 over 8, meaning that we're still at 0.8 as a total survival from 8 to 11. So we can extend this line on our survival curve now such that it goes all the way to 11 with a survival rate of 0.8. So you're probably thinking, well, what use was that? No, that didn't actually change anything. And you're right so far, but when the next wombat dies, the number of wombats at risk is not 8 anymore. It's actually 7. We don't have 8 wombats at risk because one of them we no longer have in our study. So instead of being 8 minus 1 over 8, it's now 7 minus 1 over 7. So 6/7 instead of 7/8. And that is going to multiply into the previous survival. And guess what? It's not 0.7 anymore. It's actually going to be less than 0.7. It's going to be this value here. And you might have noticed a bit of a trick I just did there. Instead of multiplying this fraction with each of the previous fractions we calculated, we can just multiply this current fraction with the previous survival value, because that previous survival value actually carries in it the product of each of the previous fractions from this formula. So let's clean up these previous formulas so you can see that it's actually just easier to multiply by the previous survival value. So this most recent wombat to die actually made the survival curve drop a little bit more than the previous 2 wombats. And that's because it represents a larger proportion of the remaining wombats, purely due to that wombat that was censored before it. So we can continue that on for 15 to 20, noting that 2 wombats died at time 15. So the fraction there, of course, is going to be 6 minus 2 over 6. So that's 4/6 times the previous survival value. And that'll give you the new survival value. Here we have a time point at t equals 20 where there was a wombat that died and a wombat that was censored at the same time. So I've not actually seen this explained very clearly on the internet anywhere else, but I did find out what to do in this situation. And you actually consider the death to have happened first. So there was 1 death out of 4 wombats at risk, not 3 wombats at risk. Anyway, so this continues all the way through to the end, and we've got our complete survival curve. Now, the cool thing about having this curve is that we can easily find things like the median survival time by just drawing a horizontal line from survival being 0.5 and finding where it hits this curve. And in this case, we can see the median survival time is 15 months. And we can also find things like percentiles. So you can see that the 90th percentile survival is 4 months. Now, some research might actually call this point the 10th percentile, given that it's at the low end of survival times. But most research will still call this the 90th percentile, and in brackets, they'll make sure they specify worst case. So it's the 90th percentile, sort of worst case outcome. And you can also find things like, say, the 25th percentile, which in this case is 25. Now, of course, these percentiles get more accurate when you get more data. And in our example, we only have a few observations, so it does make these estimates a little bit shaky. Nonetheless, it's good for an example. So we're going to have a look at confidence intervals now, shall we? So here we go. Confidence intervals. When you create a Kaplan-Meier curve in a statistical package, it won't just give you the curve. So there's the blue curve that we just created. It'll also give you what's called confidence intervals. And this might be a 95% confidence interval for the survival curve. Now, how do we actually create them? If you don't care about how they get created, then you can buzz along to the end of the video where I show you just how to create them using R code. But if you're like me and you want to actually understand what the hell's going on and how do they create these confidence intervals, then let's do this. It's going to get statsy. So the first point to think about confidence intervals, this involves a bit of an understanding of what confidence intervals are. we have here a proportion, right? A survival amount at each point is a proportion out of the total that has survived. And we should know that generally when we're creating confidence intervals, the thing under the square root here is what's called the variance of a Bernoulli distribution, or in normal person's language, the variance of a proportion. So if we take the square root of that, that's the standard error, and we can create a confidence interval around our estimated proportion, which we might call P with a hat on it. But it's a little bit more complicated than that. So the survival at any given point, we know we've done this already. This is the formula for survival. It's the product. This little bit underneath the product just says for all the values of t that are less than or equal to the one we're looking at. So we're going to first just turn this proportion into p hat just to make things a bit easier for us, so we don't have all these n's and d's hovering about the place. So p hat relates to that proportion that have survived effectively. Now we're taking the log of both sides. The reason is it's very difficult to find a variance of something that's inside a product, right? Ultimately, we need to find a variance. So if we take the log, a little bit of basic maths tells us the log of the product of a few things is the same thing as the sum of the logs of those things. Some basic log laws at play there. Okay, so that's the first step. Now we need to find the variance of this log of the survival. The variance of the log of the survival is equal to the variance of this whole thing, the sum of ln p. That if each of the deaths that occur to our wombats are independent of the ones before it, the variance of the sum of a lot of objects is actually the sum of the variance of the individual objects. Okay, that's a basic rule of variance. Like the variance of A plus B is actually equal to the variance of A plus the variance of B, but only if they're independent. So if indeed they're independent here, we can actually move along to say, well, this is the sum of the variance of each of these proportions. This is where we start getting things that looks quite nice for us, because the variance of a proportion, we know that. That's actually the thing we saw before, which was the p times 1 minus p over n, right? It's a little bit more complicated because we have the log of a proportion. So how do we deal with that? More stuff? Check this out. This is what's called a Taylor series. Well, I'm not going to explain what Taylor series are because I don't want to go on a mathematical journey necessarily on this video, but I'll give you a link in the description for a really good video on Taylor series. But basically when you have the variance of a function of x, it becomes effectively there's a differential evaluated at the mean all squared times the original variance. Now, I appreciate this stuff is hectic for a lot of people that haven't really had exposure to this, but for the boffins, I thought I'd do this anyway, right? This is what's happening underneath the hood when you're finding confidence intervals. You need to find the variance first. So the variance of the log of x is 1 on x, and we would evaluate that at the mean here, which, if we're talking about the proportion, is the sample's proportion itself. That's p hat. So it's 1 on p hat squared, and then we multiply by the variance of p hat finally. And if we then substitute back in what p hat was, we get this cool thing down here, which is that the variance of the log of p hat is actually equal to d over n times n minus d. Okay, wow. So there's a lot there, but what we've done now is allowed us to get to this point where we have the variance of the log of the survival is actually equal to the sum of this stuff. And now that we have the variance of the log of survival, we can construct a 95% confidence interval for the log of survival, which, as you might know if you've looked at confidence intervals, is the log of survival plus or minus z. Okay, if we're assuming that it's a normally distributed confidence interval, which we can do, I think, when n gets large. Here, n is probably not sufficiently large for us to do this, but we're going to do it this way anyway, times the standard error of the log of st, which is just the square root of all that junk. So we now have the actual formula we're going to use to find the confidence interval for the log of s. Wow. Okay, well, here's a table that I've constructed to show how I actually calculated the upper and lower values for the survival. You can see that I needed all those N's and D's for each of those time periods. I then calculated this D over N times N minus D for each of those time periods. Then we needed to log everything. Wow, so the log of the survival is just the log of this first column. The variance of the log of survival, if we use the formula that we just saw, the variance of the log of survival is just the sum of all of those, that quotient, D over N times N minus D. It's that quotient summed up. So it's this column over here that we're going to sum up into the column here. So you can see we've got all of those summed up. We've taken the square root in this next column, and then we've used that formula to find the log of the lower limit for the log of survival and the upper limit for the log of survival. Now, it's actually important to note, I've got little red zeros here because technically the upper limit for these ones is going to be greater than 0. And we know that if we've logged something such that it becomes a number greater than 0, then that original thing that we logged must have been greater than 1. So that's going to be a problem if you think about what that means. The survival can't be more than 100%. And this is where this particular version of the standard error needs to be tailored a little bit, because we can only have at most a log survival of 0, such that when we raise things into the exponent, because we're going to try to get our survival back again, right? So if it's the exponential, if we exponentiate these, we'll get our survival back. And you can see that the upper limit for these survival curves is 1, 1, 1, 1. It can't be higher than that. It doesn't make sense for our survival to be possibly greater than 100%. So that's an interesting point to note about these confidence intervals. There are actually options, and we'll explore them a little bit more when we look at the R code in the last section of this video. But there are options where you actually take a double log or log of the survival. And in that instance, we never get a situation where we go up to, where we push past 100% and have to bring it back in. So I will explore that in the final section of this video, just to show you that there are different versions of these confidence intervals. But this is the default confidence interval you will get in the statistical program R. And we'll be able to see that I'll replicate this using R code later on. Okay, time to look at the Logrank test. Now, the Logrank test, what it does is it assesses whether the Kaplan-Meier survival curves from two subpopulations are significantly different from each other. So let's say we actually had a combination of these wombats being men, let's call them male and female. So wombat F, G, J, A, and E are all males, and all the others are females. And just looking at this data, it seems like the male wombats seemed to die a little bit quicker than the female wombats from mange. So how can we compare the experience of male wombats to female here? Or more specifically, how can we compare the survival curves? Are these two survival curves significantly different from each other? And you can see what I've got here. I've got the two survival curves, sex equals 1 and 2. So that's just basically doing the same thing we just did to create the curves, but doing it separately for the male and female data set. So our null hypothesis when we do a Logrank test is that the male and female survival curves are equal. And we're going to try to see whether there's enough information to reject that null hypothesis. So again, if you don't care and you just want to use the R code, feel free. I'm totally understanding of that. But if you do, like me, want to know how the hell this test works, then let's check it out. So the first thing we need to do is find the time points where there are deaths. There are deaths at time 4, 6, 11, 15, 20, and 25. There's no death at time period 8, so we don't really have to worry about it. It will affect some of the other numbers, but it won't actually involve itself in the calculation here, as we'll see. So here are the number at risk in the green part of this table. The number at risk of the male wombats, the number at risk of the female wombats, and the total number at risk. We can then look at the observed deaths at each time period. At time period 4, there was one male wombat that died. At 6, there was another male wombat that died. One female died at 11, 2 males died at 15, and then there was 2 females that died later than that. So the total number of deaths was 7, meaning that 3 of these 10 wombats were censored. So how do we find the expected, let's just say, male deaths for each of these time periods? We first look at how many wombats died, and we say, all right, at time period 4, there were 5 males at risk and 5 females at risk. So if there was 1 wombat that died, we're expecting out of that 1 wombat, half of those wombats to be male and half of those wombats to be female. Now, that clearly doesn't make sense when you're talking about a single wombat. So you can read those like a probability, which are equal because there's the same number of males and females. At the second death, there's actually more females than males, right? There's 5 females at risk and 4 males at risk. So if you hear that a wombat died at period 6, your expectation should be higher around it being a female wombat than a male wombat, right? And of course, it turned out that, in fact, the male died again. So by time period 11, you can see that the expectation has risen quite significantly for females because none of them have died yet, and the male population's dwindling. So that's how this works all the way through, right? You've got the expected male deaths and expected female deaths, and you can use these formula up here, but I've just tried to introduce the intuition behind these formula. It's the number at risk of that particular sex divided by the total. So that's the proportion of wombats at risk that are male times the number that died. And that's the proportion of wombats at risk that are female times the number that died. So what happens then is we can construct this chi-squared statistic. And for those that are used to chi-squared tests, this will be somewhat familiar to you. It's usually something to do with the sum of an observed minus the sum of expected, all squared, divided by the sum of the expected. And because we're actually summing all these up, there's all these annoying little summation signs in here, but it's the same idea. It's one of these hideous equations that has a very simple calculation if you just have a table, right? The total male deaths was 4. The expected male deaths was 1.897. So we go observed minus expected, 4 minus 1.897, all squared, divided by 1.897. And we do the same for the females. 3, which is the number of females that died, minus the expected number of females that died. So it's funny that we get 5.1 as our expectation for the number of females that died. You can see that that's not possible because there was only 5 wombats to start with that were female. But it's just a way of indicating to us that at each of these time points, we were expecting the females to die, but they weren't dying. The males were dying instead. So these numbers started getting really, really large until they finally did die. So when you sum that up, you get 3.119, and we can check the critical value of chi-squared because it's a 1 degree of freedom test in this instance. There are 2 different categories, so k minus 1 gives you 1. The critical value at the 5% level of significance is 3.841. So as the test statistic's less than 3.841, there's not enough evidence to conclude that male and female survival curves are different. So you'd be looking at the chi-squared value and you're comparing it to the critical value that you would get from a chi-squared table. So when the calculated value is greater than 3.841, we could reject the null hypothesis. But as it was not greater, we could not reject. So that's interesting. It seemed like females definitely had a better survival rate than males. But because the data is so small, we've only got 5 observations, even with this, it couldn't show that females are significantly different to males in terms of their survival curves. You'd expect that when you have more data, this would be able to reject a lot easier. All right, now, there is a slightly alternate chi-squared calculation that gets made, and in R, they do it slightly differently. For the sake of completion, I'm including it here, where instead of the denominator being the sum of the expected terms, it's actually the sum of the variance of the expected term here. So look, if you care about the exact formula they use in R, then this is it here. It's really like full on, but it can be done. And I'll show you if you want to see my spreadsheet, this exact spreadsheet where I calculate manually what they get in R, then you can go to zedstatistics.com and download that spreadsheet, and hopefully that would make a little bit of sense to you. Anyway, right now what we're going to do is have a look at doing Kaplan-Meier estimation using the statistical program R. Now for this, I actually need to get out of this program because I'm going to use RStudio. So it looks like this. Now for those that have never used R before, it's really an amazing freeware program. You can download it from, I think it's CRAN, C-R-A-N. If you just type in R software, you'll figure out how to download it. You need to download the basic R package, but I actually also download RStudio because it allows a bunch of point and click functionality that I like to use. Anyway, so this R code again is going to be put up on my website. That's zedstatistics.com, the letter Z, then statistics.com. So you can grab this and do whatever you want with it. It's very simple here though. We need some packages we need to install such that we can do some survival analysis. One's called survival and one's called serve-minor. So we load in those packages. Now we're going to load in our data, and it's that same wombat data. Here's our time, which is the time of death. Well, the time for each of the wombats in our sample. And to run this, I'm just pressing Control and Enter. But for those of you familiar with R, this won't be too confusing for you. But we've got time status. That's our censoring, well, essentially whether they died or not. 1 being died, 0 being censored. And they're all in order, right? The first observation was death, the second was a death, the third was a censoring, right? Sex 1 and 2 labeled correctly for all of the times, corresponding ones for time. So then we've got our DF, which is our data frame, time, status, and sex. So if we just write DF, we'll be able to have a look and inspect it, see what it looks like. Time, status, and sex down the bottom here looks pretty good. Basically what we had in Excel. Okay, now to do the survival curves, we need to create a fit object, which uses the function serveFit. And then we're going to create a summary of fit. And you can see we've used the serve function using time being the time variable and status being the death/censoring variable. And the summary is as follows. This looks very similar to what we got manually. You can see that the lower 95% confidence intervals there, the upper confidence interval there is all there as well. And that's exactly what we got when we did it manually. And if you want to sketch it, we can do this survival plot, ggsurvplot. And yeah, there we go. There's our survival curve for all of the wombats put together, and our confidence interval, which looks very similar to the one I created. It has that weird scenario. You can see that it actually increases by the last little bit, which is because of the number of observations. Because that's so low, you might get strange things like that. So this is the curve and the confidence intervals done using the log confidence intervals like we did in the example. If you recall, I said that sometimes you might want to use a log, and often textbooks will prefer this for the very reason that we don't have to truncate our confidence intervals to make sure that it maxes out at 100% survival probability. So there's a bit more, it's a bit more natural when you do a log. I haven't included the real maths behind this just because this video is getting a bit long. But it's relatively simple maths. You're taking the log of the negative log of the survival, which essentially, if you think about what happens there, you're going from a survival probability from 0 to 1. If you take the log of the negative log, that number goes from negative infinity to positive infinity. So you can never reach a sort of end point that's a fixed end point. And you can see right here that the survival proportion is not 100%. It's always going to be slightly less than 100. So yes, this is actually preferred by, I've seen a few textbooks like the log version better than the log. And you can see it also doesn't suffer from the quirk of the upper limit increasing by that final step. You can also do the plain version as well. It's exactly the same thing. You can see it's just conf type, confidence interval type is log instead of, well, if you don't specify, the default is just log. Interesting to see how they differ. Let's have a look at the third one, which is just the plain. They do differ a little bit, particularly because the data set's small. So plain would mean you've actually undone the log before you've calculated the confidence intervals. It would be a perfectly symmetrical confidence interval, that one, notwithstanding the truncation, which could happen on both sides in that case. So it's quite temperamental, I would say, the plane confidence interval. I would go with log. If you've got a particularly large data set, I don't think they're going to make too much difference, but the log I think would be the most preferred. Now, here's the analysis done by sex. So again, we could create a fit object. The only difference is you see we've got this little tilde which says we're actually going to do this split by sex. So let's create fit4. That's the new object. ggservplot is going to allow us to create this plot split by sex. And that's exactly how I got that plot initially in our earlier in this video. And finally, we can do this thing called servdiff, which will allow us to test whether males and females indeed are different. And you can see we've got a chi-squared stat of 4.2, which is different to the one I got because remember I said that they do calculate it differently. But that's all I wanted to show you. You can steal the code if you like. It's up on the website. But realistically, that's it. I've covered quite a lot of stuff on Kaplan-Meier. This video has taken me a long time to produce. If you like what I do, please share it around. Look, you can like and subscribe and do all those kind of things. But if you know some people that are into stats, feel free to send this on. We're going to look next at the more general survival curve and the hazard function. Thanks for watching, and I'll see you again at the next one.